Hello friends, I welcome you in lecture number 7 on permutations and combinations. In this lecture we are going to discuss one example on combinations with repetition. In previous lecture we have seen one result about combination with permutations, which says that suppose we are interested in the R objects of capital M types. To select R objects of capital M types, the number of ways or selections are given by R plus M minus 1 C M minus 1 or R plus M minus 1 C R, where combinations with repetitions are allowed. Suppose we are interested in the selection of R objects of capital M types with repetition allowed, then that number is given by R plus M minus 1 C M minus 1 or R plus M minus 1 C R. So we are going to discuss one example which is based on the application of this result. Here the question is, how many solutions does the equation x plus y plus z equal to 11 have, where x, y and z are non-negative integers? It is given that we have to find out non-negative values of x, y, z which satisfy this equation. In other words, we have to decide the total number of non-negative integer solutions of this equation. We know that this equation x plus y plus z equal to 11 has infinitely many solutions, but if we count only non-negative integer solutions, then they are finite in number, and using this formula we can decide the exact number of non-negative integer solutions for this type of equation. So first we have to decide that what we should consider as R, that is how many objects we have to consider and what are the type of objects in the given problem. So before deciding this small r and m, first we consider one trial solution. Here suppose I consider x equal to 3 and say y equal to 2, then 3 plus 2 5, so I have to consider z equal to 6. By trial and error we find that this x equal to 3, y equal to 2, z equal to 6 is one non-negative integer solution of this equation. Now suppose I represent this x, y and z values by star. Suppose I consider 3 stars for x, 2 stars for y and 7 stars 1, 2, 3, 4, 5 and 6. 6 stars 1, 2, 3, 4, 5 and 6 for z, 2 stars for y equal to 2 and 3 stars for x equal to 3. So this is one solution by trial and error, and here I have taken 2 bars or 2 dividers where this object is changing. Here we are changing from x to y, so I consider divider here, and here we are changing from y to z, so I am taking another divider. Now if you observe, suppose I change the position of divider here. Suppose instead of putting divider at this place, suppose I am putting divider at different places. Suppose I put one divider here and another divider here. Then up to this I have 2 stars. So suppose I consider x equal to 2. Now whenever we have divider or bar, we change the type of object. So we change from x to y. So I have 1, 2, 3, 4, 5, 6 and 7. That is y equal to 7. And because I am having a bar, I am changing from y to z, and there are 2 stars for z. And you can see 2 plus 7, that is 9 plus 2 is 11. So this is another solution by changing the position of dividers, we obtain another solution. So from this we may have the idea that we have to decide the number of ways of putting these dividers or bars among all these positions. The total number of positions are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and 13. That is 2 dividers and plus 11 stars. So now it is clear that we have to select 11 objects or items of 3 types, that is m equal to 3. 3 types are first type is for x, another type is for another variable y, and third type is for variable z, and we have to find out 11 items of 3 types. So here we have 2 items of x type, 7 items of y type, 2 items of z type. Similarly here I have 2 items for x, 7 for y and 2 for z. So this is the problem of finding the number of ways we can select these 2 bars or 2 dividers out of this 11 plus 2, that is 13. So we have total 13 positions and we have to count the number of ways we can select these 2 dividers out of this total 13 dividers. So this 13C2 will give us the total number of non-negative integer solutions to this equation. So this is very easy. We don't have to remember this formula also if we are able to understand this logic, that first I consider one trial solution, then because I have 3 variables I am taking 2 bars, and by changing the position of these 2 bars I am able to decide different solutions. So the problem of finding non-negative integer solutions reduces to the number of ways we can put these 2 dividers among all these total 13 positions. Or we can understand that here we are interested in the selection of 11 objects of m equal to 3 types. Therefore we can use this formula r plus m minus 1 c m minus 1. m minus 1 is 2 and plus 11, that is 13 c 2, and this will give us the total number of non-negative integer solutions. So this is very interesting question. Using the combinations with repetition, we are able to decide the exact number of non-negative integer solutions to the given linear equation in x, y and z. So you have to write systematically. Here I have written, to count the number of solutions, we note that a solution corresponds to a way of selecting r equal to 11 items of m equal to 3 types, where x items of type 1, y items of type 2 and z items of type 3 are chosen. That is, we have 3 variables. Therefore, the number of non-negative integer solutions is equal to the number of ways of choosing r equal to 11 items of m equal to 3 types, and is given by r plus m minus 1 c m minus 1, that is 13c2, and 13 into 12, this will get cancelled, and we have total 78 non-negative integer solutions to the given equation. This is one possible equation. So we have this type of exactly 78 non-negative integer solutions for this equation. So in this way we can apply this concept of generalized combinations or combinations with repetition in counting the number of non-negative integer solutions to this type of linear equation. So this is all about this session. I hope you like it. Thanks for watching.